This is Regents Review Unit 11, Organic Chemistry. Recall that organic compounds are compounds that contain carbon and hydrogen. And there's a specific type of organic compound that contains only hydrogen and carbon, and we call those hydrocarbons, containing, again, only hydrogen and carbon. Carbon is unique. It has 4 valence electrons, and so it forms 4 bonds to get a full valence shell, as in the example here for methane, CH4. In naming and formula writing with organic compounds, we're going to use table P and table Q. Table P is our prefixes, based on how many carbons we have, and table Q is the homologous series of hydrocarbons. Again, you see the word hydrocarbon containing only hydrogen and carbon. And so the series names we have are the alkanes, the alkenes, and the alkynes. And what makes them different is alkanes are these saturated hydrocarbons, all single bonds. Alkenes are unsaturated, having a double bond. And alkynes are also unsaturated, having 1 triple bond. And the general formula we have here to figure out how many hydrogens correspond to how many carbons is listed here, where N is the number of carbons. So for example, pentene has 5 carbons and 10 hydrogens. Pent, go to table P, it has 5 carbons, and then ene, I find the series alkene on the table here, and I plug in 5 for N. So 2 times 5 is 10, and that's why pentene has 10 hydrogens. Working backwards from the formula, if you're given a formula here, or a structural formula, it has 2 carbons, so 2 carbons is eth, and then we have a triple bond, so a triple bond indicates a ending for YNE, so the name of this compound is ethine. So how do we determine the type of hydrocarbon? As we did, we count the number of carbons. If the number of hydrogens are double the number of carbons, it's an alkene. So this is my little trick here. So instead of plugging into every formula trying to figure out which one it is, I know the alkenes have double the amount of hydrogens. So if it's double the amount, I know it's an alkene. If it's more than double, it's an alkane. And if it's less than double, it's an alkyne. So for example here, C5H12. Well, 5 times 2 is 10. That would make it an alkene, but this is more than double. So I know it has to be an alkane. And so I know that I can plug it into that formula. So 2 times 5 is 10 plus 2 is going to give me 12. So now that I know it's an alkane, I could name that example. So 5 carbons, going back to table P, is our pent. And then we know it's an alkane, so the name is pentane. We have different formulas that we can use. We have the structural formula here, listing out how the carbons are attached to the corresponding hydrogens. We have a condensed structural formula, essentially pulling out the bond lines. So it's each carbon and then the hydrogens that are attached to it. So this would be CH3 as indicated here. The next one is CH2. And then the last one is CH3. And we have the molecular formula, which just indicates how many carbons and how many hydrogens we have, but it doesn't tell us the orientation for them. So these are all different ways to represent propane. Recall that when we named unsaturated hydrocarbons, so these are the alkenes, the double bond, or the alkynes, the triple bond, you have to give the location of the bond. So we can count from left to right or right to left. You have the option because there is no left or right side. But once you start counting from one direction, that is it. And we want to give the location of the bond if there's more than one possible location. So here is 2-butene. The molecular formula is C4H8. So it has 4 carbons and 8 hydrogens. And the 2 indicates that the double bond is on the second carbon. So 1, 2. If I go right to left, 1, 2. So in this case, it doesn't matter which direction I go. But if I had an extra carbon here, for example, I want to go left to right, keeping it the lowest possible number. So we want to give this bond number the lowest possible number in our name. And then our condensed structural formula, again, is just taking out the bond line. So it's CH3, then CH, as indicated here, another CH, and then CH3 here. So just repeating, if we have a double or triple bond, and there's more than one location that it could be in, you have to give that location, giving it the lowest possible number. So try it left to right and right to left, and assign that number the lowest possible value. Isomers, the word iso means same. Isomers have the same molecular formula, but a different structural formula, and that results in different properties. So, for example, these are both isomers of each other. They both have the same molecular formula of C4H10, so 4 carbons, 10 hydrogens. But we can see this is a straight chain alkane, and here is a branched alkane. And so we know if it's an isomer by first looking at the molecular formula. If that's the same, but the names are different, we know it's an isomer. So how do you make, if they ask you to make a isomer of a straight chain like butane, simply take one of the N carbons and hydrogens and then attach it as a branch on one of the middle carbons, as we did here. For a unsaturated hydrocarbon, for a double or triple bond, these are even easier. Just move the location of the bond. Just make sure you're not moving it to the same spot on the other side of the molecule. So, for example, here, if this is 1-butene, it's on the first carbon, I can just move it 1 over to the second carbon and have 2-butene. Again, notice that the molecular formulas are the same, but the names are different because these structures are different. How do we name the branched alkanes? First thing you do is you locate the longest string of carbons in a row or connected, and that would be our parent chain. And so in this case, this one's going straight across. We have 1, 2, 3, 4. So 4 carbons from table P is going to be a but. The branches are always going to be alkane, so it's going to be ane ending. And then I want to figure out what is the location of my branch. And so we can see that we have this branch here sticking off the parent chain, and this is a 1-carbon branch. So 1 carbon is going to be meth from table P. And for branches, we add the ending YLE to indicate it's a branch. So we have this methyl branch. Now, what location is it on? So what carbon is it on? Just like in the double or triple bond, when we want to number the location, we want to give this the lowest possible number. So we can try right to left and see that it's on the 1, 2, the 3rd carbon. If we go left to right, it's on the 1, 2. It's on the 2nd carbon. So it's 2-methylbutane. So we have a methyl group on the 2nd carbon of a butane parent chain. In this example here, you'll see that we still have butane as a parent chain, but now we have a 2-carbon branch. So it's not methyl-methyl because these carbons are connected together. It's 2 carbons together, so from table P, 2 carbons is going to be eth. So it's an ethyl branch, and it's also on the 2nd carbon, so it's 2-ethylbutane. This is different from this situation here where we have 2 separate methyl branches. Right, they're 2 separate 1-carbon branches. So this is a methyl-methyl, and instead of saying the same name twice, what we can say is dimethyl. And then we want to give the location of those methyl branches. So we have both branches on the same carbon, so they're both on the 2nd carbon, so it's 2,2-dimethyl. So you always want to make sure that you're given the location for each branch. This way, if you were given a name, you could work backwards. So if I was given this name and asked to draw that structural formula, what I can do is write out butane first, which is the 4 carbons, and then on the 2nd carbon, I have a methyl group, and it says di, so I'd have 2, so methyl-methyl. On table R, we have this list of functional groups, and they give you the class of compounds, so things like alcohols and ketones and esters, which are our smells. It shows you the functional group, what it looks like. They give you the general formula, and I find this useful. The R represents carbon, so you can tell then, is this a terminal branch? So is this something that's on the end of a string of carbons? Or in this case here, like the ether, I have carbons on both sides, so this is somewhere in the middle of the compound. So if you're given a substance, the first thing you want to do is identify the class of compound in your example. So if you look here, I see Br and another Br. So I look on my functional group list and I find Br. I see it here. So this is a halide or halocarbon. And then I look and see how did they name theirs, and I look at mine and see what's different. And typically it's different by a number of carbons. In this case, instead of the chloro, because they have chlorine here, we have bromo, because that's bromine. So we have a bromine and a bromine. So I look at their name. They name theirs. They have 1, 2, 3 carbons. So that's where the propane is coming from. And then the 2 is the location of the chloro functional group. It's on the second carbon. So if we look here, we have bromo. One's on the first carbon, one's on the second carbon. So this is 1, 2, and we don't like to say the same name twice, so it's 1, 2 dibromo. And then the 2 carbon parent chain, which would be ethane. So again, use the examples they give you and then see how yours differs and then adjust that name based on the number of carbons. Okay, let's see an example here. First thing you want to do is locate the functional group. So I look at my compound here and I see that in this molecule that I have a C double bond O. That's my functional group. And I locate that. C double bond O. So I have two choices. I have the aldehyde or the ketone. The aldehyde, if you look at the R here, only has carbons on one side. So an aldehyde is a end functional group at the end of the molecule. And whereas a ketone, we have R's on both sides, means we have carbons on both sides. So this is somewhere sandwiched in the middle. And if you look at this example, that's where our C double bond O functional group is. So I notice it's a ketone. Now look at their example. How did they name theirs? I see pent, 5 carbons. 1, 2, 3, 4, 5. So that's where the pentane's coming from. And I'm adding the one for the ketone. And then 2 gives me the location of that functional group. It's 1, 2 on the second carbon. So I look over here, and if I went left to right, 1, 2, 3, this would be on the third carbon, but we always want to give it the lowest possible number. So going right to left, it's on the 1, 2. It's on the second carbon. So it's 2-butanone. Next example, C double bond OO. I locate that, and I see I have really two choices, organic acid or ester. This is somewhere in the middle. It's not on the end. The organic acid has carbons only on one side, so that's on the end. So this must be an ester, having carbons on both sides. Once I locate that, I want to look at their example and see how they named theirs. So I see prop. Prop is 3 carbons. I'm trying to find 3 carbons in a row, and I see I have that here, 1, 2, 3. So I have 3 carbons on this left side here, which is attached to the C double bond O. And then methyl is 1 carbon, and there's a 1 carbon there on the other side of this O. So the O is essentially separating this into like 2 names. We have the methyl side, and then we have the propanoate side. So now let's look at our example. We have 1, 2, 3 carbons attached to this here. So that's meth, eth, prop. That's still prop. So it's a propanoate, just like the example here. And then on the other side, we have 1, 2 carbons. So instead of the methyl like we had in the example, we have 2 carbons. So table P says ethyl. This is an ethyl propanoate. So use this table to your advantage if you're asked to name these structures. And lastly, going through the types of reactions we have, you have to be able to identify these. So a combustion reaction is when we're burning something. So we have some sort of hydrocarbon in the presence of oxygen, and we create carbon dioxide, water, and energy. If you're asked to create these things, these are your combustion reactions. They're actually on the top of table I, and so you can use those as a guide because it's the same format. It's, again, this hydrocarbon or some sort of organic compound, oxygen making CO2 and water. The addition and the substitution reactions are where they often ask you to build these things. So they'll give you the reactants and say complete the reaction. So addition reactions, we have a double bond that can break, and it gives us 2 extra bonding sites to attach a halogen, in this case the 2 bromines, and they can attach here just like such. Notice that the number of bonds is still the same for carbon. It has 1, 2, 3, 4 here, and 1, 2, 3, 4 here. We can't change the number of bonds. But because that double bond breaks, we can add, hence the name addition, we can add these halogens. Versus the substitution single bonds, they have a alkane. So because they have single bonds and it's already full with hydrogens, we can't add these halogens, these chlorines here, or bromines, or fluorines, etc. What we can do is we can switch or sub one out or substitute out one of the hydrogens and put in a chlorine, as we did here. So the hydrogen came out and bonded with chlorine to make HCl, and then this 1 chlorine came in here and took the place of hydrogen. So again, the addition has the unsaturated alkane or alkene or alkyne, and substitution is a single bond, it's all alkanes. Esterification is making an ester, so you can look for, using table R, look for the ester. These make our smells. And we use an organic acid and an alcohol to make these esters. Fermentation is making alcohol, so we're using an enzyme to break down sugar into alcohol and carbon dioxide, the bubbles. So how do you know this is fermentation? You're making an alcohol. How do I know it's an alcohol? Table R, here's my functional group OH, attached to some sort of organic compound. Saponification, we're making soap. It will often say soap as a product. We're using fat and a strong base, sodium hydroxide, to make this glycerol and our soap. Polymerization, poly means many. We take many single monomers, like an individual link of a chain, and then we're just going to repeat that over and over and over, connecting these, making these long chains. So we can look for the N representing a very large number, or it may actually have a very large number, like 1,000, for example, indicating that this thing is repeated over and over and over, hence the poly. These are things like plastics, etc.